case they're not being recorded. Okay. The multi-instance retrieval had a particular interesting case this year. In the leaderboard, we were not very clear about the exact metric for ranking. We have two metrics, the standard MAP and NDCG. We also have text to video and video to text. And it's very interesting that people optimize for one or the other. So we're going to have a set of joint awards. This is explaining where the joint awards come from. And also this year, if you have been with us, you know that in some point in 2020, we talked about something we called the supervision level scale. That means every method was requested to self-declare on all the leaderboards, what have they used in producing these results. This was suitable for anonymous submissions, and it was some sort of a discrete three-dimensional scale. So as an example, on one of these scales, it was what do you use in pre-training? So if you had used only kinetics and how to 100 million, then you report number 2. If you've done some self-supervision on another large-scale public data set, it's 3. If you've done self-supervision also on Apex, so you utilized more the annotations, you've done 4. And if we are using a private data, we still encourage people to submit to the leaderboard, but we ask them to mark these as 5. And similarly, we have what type of annotations you've used. That was the second scale. And the third scale was whether you've trained only on chain and only on chain and val. Our objective is to allow everybody to submit and compare, but also to know the distinction between these two different awards, two different types of papers. And we this year have noticed some changes where we are ranking, but the pre-training or clearly these are not directly comparable because people are using different leaderboards. And I'm using this particularly for the action recognition challenge. You can see that the winners have clearly reported 5. They have used a private dataset, not available to the community. And accordingly, they've won the challenge. The second ranking haven't used that. This is something we as organizers are going to discuss for next year. Currently, we still are awarding people by the rank only while they still self-report. Now with this change, let's see how we can think about our awards and our rankings differently. If you're interested in discussing this with us, if you're part of the EPIC community, reach out. We're keen for ideas. We're still keen for everybody to submit, but also a fair set of results. So this is hopefully coming in 2023. Yeah, as we said, action recognition was really hard to beat. We have 2 people who've beaten last year's deadline, but we have baseline, but we have a number of people who submitted and could not beat the baseline. So this is becoming really a difficult baseline to beat. Next, we're going to go into the awarding of the certificates and the WinnersTalks. So basically, please react in person or virtually. Is that okay? That's what we're going to do. Go ahead.
So good morning. I'm Anurag from Google. And
you might want to be closer to the microphone. That's the only thing, yes.
And on behalf of our team, I'm going to be talking about a winning entry to the Action Recognition Challenge. So our entry is going to extend our sort of paper, which is actually going to appear at the CVPR. It's called Multi-View Transformers for Video Recognition. And it's going to be 2 tomorrow, actually. So I'm first going to give a brief overview of this model next, and then I'll talk about how we extended this to sort of win this challenge. And so the main sort of extensions we made is now the model. So now the model is multimodal because we also use audio and R and flow as well. And we also scale up the resolution and pre-training as well. So just to give a sort of motivation, some modeling inputs at sort of multiple resolutions has been a core idea in Vision. So even some like really old papers such as HUG or in like the pyramidal structure of like CNNs. So in this work, our goal is to sort of model sort of multi-scale spatial temporal sort of data by sort of creating different views of the input. And so by this, we mean we sort of create sort of different views as sort of parallel streams. And then we sort of have these sort of lateral connections between these different layers. So in the MTV paper, the sort of views are constructed by tokenizing the views are constructed by tokenizing the input with different tubelet sizes. So for example, small tubelets have sort of many tokens along the temporal axis. and they can capture sort of fine-grained motions. And on the other hand, sort of large tubelets, there are very few tokens along the temporal axis, and they sort of capture more global scene context. So in this challenge, we sort of have we have a multimodal version of AMTV. And here sort of each view is rather a separate modality. So we have RGB, we have flow, and we have audio as well. So in our sort of AMTV model, we can use sort of different encoders for processing each view. And what we actually found best to work in the AMTV paper and what we used here was actually you have as like a sort of deeper transformer encoder for the model, a deeper transformer for like the view with more tokens. So for example, if the name here, for example, is B/2, S/4, and TI/8, means, for example, we use a base model with sort of tubelets of size 16 by 16 by 2, and a small encoder for tubelets of size 16 by 4, and sort of a tiny one for tubelets of 16 by 8, and like so on. And you can see in the paper sort of that motivates the choice for doing this because it was the best in terms of the sort of accuracy and speed, like trade-offs. So now when you have now we have different modalities, we sort of have the same convention as well. But now we have different modalities for each view as well. So for example, what we also found was it was best to use a deeper encoder for RGB, and this is quite intuitive as well, because the RGB is the one that matters the most. So when we start looking at the effects of different modalities, we can see that RGB alone is actually quite strong. In fact, I think this is like sort of the highest single model results on the validation set as well. And then when we sort of fuse RGB and audio or RGB and flow, that sort of improves further. And sort of the best performance that we got from a single model was when we had sort of RGB flow and audio. So another important aspect sort of to achieve higher results is also to scale up the sort of space to increase spatial temporal resolution of the inputs. So in all cases, we're using 64 frames, and then when we have even more tokens by increasing the spatial resolution, we sort of improve further. This is also consistent with some sort of previous papers and ablations that we've done in the past. And sort of the final sort of ingredient that we used was also to sort of scale up the pre-training. So we know from previous experiments that kinetics pre-training is quite important because epic kitchens are still comparatively small when you compare this to sort of other data sets. And so when you sort of pre-train a model and fine tune it, it sort of helps a lot. So you can see we improved from using kinetics 400 to 700. And we sort of got a further boost by using the weak textual supervision data set of Stroud et al. Which is also some work from Google, and this was sort of web scrape videos from YouTube. So it's collected in the same way as kinetics. It's even using the same search terms, but the labels are noisy because they're not manually verified. So putting this all together, this is sort of the results of a single model sort of entry, and that was already sort of better than last year's winner using one model. And when we sort of ensembled sort of different models, this gave us a further boost. And this was our final entry. We used two ensembles, so one for verbs and one for nouns, and we combined those two, and we found that was slightly improvement as well. And yeah, just for reference, these are all the models that we used. Yeah, so just to conclude, we use a multimodal extension of AMTV that we presenting at the main conference. And we scale up the pre-training and the resolution, and use multiple modalities. Yeah, so if you want to find out more, you can visit our poster tomorrow. And if there's time for questions, I can answer them.
Fantastic. Thank you very much. Okay. We're going to do 4 talks and then take joint questions. Right, we're going to take joint questions. We're going to take joint questions for all the 4 first set of talks. So next, we're going to move to the second on recognition. Jason, if you're with us, you can share your screen. My emails. We're ready for you.
Can you hear me? Can you hear me? Hello?
I think you might be muted. I don't think we can hear you yet.
Hello?
How do you remove thing? My laptop. Oh, my laptop is muted?
Hello? Hello, hello?
But I can't hear him even here. Uh,
Can you try speaking now?
Hello, hello,
now?
hello?
We can hear you. Just cannot get you.
No. we can't.
Hello, hello?
Go ahead.
Hello? Can you hear me? Oh, I can't hear you now, but okay.
Yeah, we're muted, but we can hear you.
Okay. Okay, I'll start. Hi, everyone. In this presentation, we'll explain the Oxford Bristol submission to the Epic Kitchen's Action Recognition Challenge. As in previous work, we want to benefit from the context when classifying action segment. Like if you see in the action sequence in here, you can use the audio and visual features to recognize the wash aubergine in the center. But if you can employ the preceding and succeeding actions, such as take aubergine or turn on tap, we can predict the action of interest more effectively. Previous work has used neighboring action segments to improve the action recognition performance. In our work, we use neighboring temporal windows instead of neighboring action segments. In addition to use the visual features in the temporal segment we want to recognize, we sample the number of features before and after the action of interest. We can also use the same technique in audio. We sample the features equally spaced along the time axis before and after the action segment of interest. This means we use background segments as well as foreground segments. This is also applied in both training and inference. Now we explain the overall architecture here. First, we randomly sample the video clip within the action of interest and use the video and audio as input. We also use the clips before and after the action of interest and use both video and audio as inputs to the encoders. These encoders produce the representation with reduced dimensionality. We then add the positional encodings and modality encodings to make use of temporal order and modality information. We also add the center embedding to features from the ongoing action, which allows the network to know the action of interest. We observe the substantial decrease of overall performance if we do not introduce this embedding. We inject the resultant embeddings with CLS tokens for verb and noun to the visual and audio transformer and use the corresponding outputs from these CLS tokens to use as our final decision. Temporal relative localization loss, which we will explain later, is also applied to the transformer output. In this work, we introduce the temporal relative localization loss to train the temporal positional encoding. We randomly sample the pairs from the transformer outputs and concatenate and put into the fully connected layer, which produces the relative distance between the two features. We tried two variants of this loss, single modality loss, which computes the distance only within each modality, and cross-modality localization loss, which always samples one from audio side and another from visual. We observed the latter results in much more additional gain than the formal, which forces the network to learn the relations between two different modalities. We also use the language model to leverage the temporal context not only between video and audio, but also between action labels. We trained the masked language model only with action labels in the train set and use it to improve the predictions of the audiovisual transformer by filtering out improbable sequences. This is a result of our method. We analyze the effect of each component by training the model with Epic Kitchen's train set and testing with Epic Kitchen's validation set. We use motion format features for visual side and auditory slow-fast features for auditory side. The performance gets better when we introduce temporal context, audio, temporal localization loss, and language model. For our final submission, we include the Epic Kitchen's validation set to train our model except the 1,000 samples which we randomly chose for tracking the performance. We ensembled the models varying the length of temporal context and using two different visual encoders, Motion Former HR and Omnivore. Our final submission results in 50.9% of top one action accuracy and achieved the second place in the competition. To summarize, we first proposed a novel multimodal framework which uses the temporal context within visual, audio, and language modalities. We use temporal windows that include both foreground and background actions. And we also propose temporal relative localization loss, which enables the network to learn the temporal distance between actions. We achieved 50.9% of top one action accuracy in the test set and rank as second place only using publicly available data. Thank you.
You don't hear us. Yeah, I noticed that. So we're moving into the second team for action anticipation. If you can hear us, it's time to share your screen. We noted that the winners, they sent us a video, which we will share later rather than now during the workshop. But we have the second team from NVIDIA. So,
Okay, so can you see my screen?
we can, and we can certainly hear you.
Okay. Okay. So hi everyone, I'm Zongmin Dai from NVIDIA and Free University of Pozzo, and I would like to share our work for the Application Video Action Anticipation Challenge. For the video action anticipation, the goal is to predict the future action labels based on the preamble observations before the action starts. In this competition, the target anticipation interval is set to be 1 second before the action starts. We propose the two recurrence modeling for this challenge. The first is the host, featured by the high order recurrence and spatial temporal attention. Another is MPNNEL, which based on the message passing framework. And we also propose the edge learnings to learn the vertex interactions. We apply the class weightings, fighting for the label imbalance, and also with our training recipe. As the ungraded modeling, force leverage high order recurrent design. For each time step, the output is computed depending on multiple previous time steps instead of the last one. And those high order information is stored in the high order queue, which is highlighted in the gray box of the figure. And spatial temporal attention learns to query the relevant information from high order queue with the decomposition attention of spatial and temporal boundaries. So the right-hand side shows our design figure diagram and also comes with visualized example shows what had been learned in the spatial attention maps. The spatial attention maps highlights the relevant information spatially, and also the temporal contribution is can be found in the temporal attention maps. MPNNEL, which is another model we use, is it first encode each frame onto the spatial graph representations and leverage the message passing framework to learn the temporal propagation. The message passing framework is composed of the message function, update function, and readout function. We implement all of them by the multi-head self-attention. The vertex of the spatial graph can be also augmented by our novel edge learning design, which are crest token projection and temporal bank. And for the crest token projection, we use the two crest token to project the adjacency batteries to augment the edges. And for the template bank, we use the query to find a suitable templates to augment the edges. Using the self-attention here can be treated as learning the information routing between the vertex by attention weightings implicitly. And our edge learning provide a flexible way to further augment the edges explicitly. Our training recipe include 4 stages. The first stage is we call the warm-up. In the warm-up, the backbone is trainable and model is allowed to access the action frames. The second stage, which is the ordinary training stage. In this stage, the training is using the normal anticipation setting. We also apply the fine-tuning stages to the models. In these 2 stages, the model is trained with the class weightings applied and in lower learning rate. The validation set is joint training in the last stage. The class weightings are applied accordingly to the appear frequency of labeling. We jointly supervise the verbs, nouns, and actions. The weightings are computed independently using the training set. And because the action is the joint probability of the verbs and nouns, so adjust the class weightings individually actually reshape the label relationship and bring additional regularization to the model. Empirically, we found it can improve the model performance significantly. And here is the results. The left-hand side is the table, include all the model family, modality, and backbone. We consider two different backbone and different modality, and using the 2 model family, first MPL and EL with the class token projection and template bank. In total, we ensemble 54 models by averaging their prediction score, 30 for RGB, 10 for optical flows, and 8 for objects, and 6 for masking RGB. All our models are consume 2.5 seconds context from the 3.5 seconds to 1 second before the action start. And our best submission achieved overall 19.61 action accuracy, which is emphasized by all the RGBs with a higher weightings. And our papers and codes are released. Thank you very much for listening.
Fantastic, excellent. We're moving now to the 3rd ranking in anticipation, and the talk is in person. So hopefully I can. Do you have the Zoom on? Are you on Zoom?
Oh, no,
You're not on Zoom. Okay.
sorry.
This doesn't fit into this one. What do you have? What do you need? You need HDMI directly? But then we don't hear him.
Oh.
The audio. I'm just checking that I'm not muted. Can you hear us online? Yes, we're fine. Go ahead.
Yeah, thanks. Hello everyone, I'm Sean from Imperial College London, and today I'm going to present our work on this year's action anticipation track. So the task of action anticipation have made great progress in terms of the dataset creation and model design. And in this work, we shifted our attention to the inherent challenges of this task, a combination of the long-tail distribution and the domain shifts. On one hand, the human actions are in nature long-tail distributed, where a large number of categories only contain a few samples. And if we propose a cross-entropy loss on its original distribution, it might lead to some severe overfitting on the tail classes. And on the other hand, for the same action that are going to be executed, their past observations might be quite different across different subjects, different teaching backgrounds and viewpoints. So in this task, these 2 issues are going to be addressed simultaneously. However, the coexistence of these 2 issues make this problem much more complicated and fears most existing long-tailed or domain generalization solutions. So on one hand, if the long tails entangle with domain shifts, there might be some superior correlation between the tail classes and some domain-specific features. And on the other hand, if the domain shift is entangled with long tails, it would be impractical to form some intra-class, inter-domain sampling to do the class level feature alignment. So in our work, first of all, we use the cross-modality matching, leveraging the external knowledge based on word embeddings to perform cross-modality matching. We assume the text embedding extracted from some language models are semantic meaningful and unbiased. And then we perform the contrastive learning to align the visual features and the text embeddings. Subsequently, we apply some domain-specific prototype learning to tackle the domain shifts effectively. So based on the feature extract from the feature extractor app, we update its corresponding entry in these prototypes in an online manner. And meanwhile, for those unseen tail classes, we use the class embeddings to update the entry. And then we perform the cross-domain prototype alignment to align the features to prototypes belonging to other domains. And finally, we apply a very popular long-tail learning method, the two-stage training, to improve the performance of tail classes. Until now, we assume we have already learned some domain-aligned unbiased feature, and then we fix the feature extractor and train a hit classifier from scratch on a balanced distribution, and it will reduce the overfitting by relaxing the decision boundary of the tail classes. And to test the effectiveness of our method, we integrated two backbones, including the temporal AGG and our transaction model into the framework and tested in different modalities. And after using our framework, the large performance gains can be observed. And to join the competition, we set different observation lengths and time steps and made an ensemble of these 4 models to get the final result. And we compare the performance with existing published work when trained early on the trend split, and also compare the same model performance on the test split. And our method have some superior performance compared with existing published work. And for joining the competition, we made an ensemble of the model trained both on training and validation sets, and also made an integration with the SOTA method proposed by the Facebook. And we compared our method with some existing long-tail SOTA methods, and it can be observed that our performs better in most metrics compared to others. That's all. Thanks.
Excellent. Thank you very much. We now have time for questions for the speakers on recognition and anticipation. So you can raise your hand if you want to ask virtually, or get to the microphone if you want to ask in person. I'm actually curious about the usage of audio for both the recognition, both the 2 teams being able to beat the baselines from last year, both used audio. So maybe let's hear back from the winners about how much do you think audio was critical in achieving the performance results. Maybe if you come here, then everybody can also hear you.
Yeah, I mean, I think you saw from our results that audio, I mean, it did improve the results a bit. I mean, the same for flow. I mean, I think for audio, what we've seen across some of the other data sets that we've tried is it doesn't always help, but I mean, it depends a lot on like the type of scene and the type of video and so on. But for egocentric video, I think it matters a lot more than kind of the internet videos that you usually see, and it's usually quite correlated to like the actual visual sort of content as well, which is not the case in a lot of the sort of other domains that we've done these experiments on as well. So in terms of like egocentric, I think it really makes sense. But in sort of other domains I've tried this on, it doesn't always like it's not always worth it, basically.
Yeah. Any other questions for Anurag?
Okay.
perhaps let's ask the same question to Jason. Again, a very audio motivated approach. How much do you think that is critical for being able to beat the baseline?
Yeah, that's a good question, actually. As I presented, if we include audio, in our case, we've had like approximately 2% boost on overall performance. I think it's also is very important in applications data set as an egocentric video data set, because like in here, like participants usually wear the like camera in here and then move very quickly. So must be like some blur in the objects if you only see them, but if you can hear it, you can actually hear some very distinguishable sounds such as water or like press the button, something like that. So it's very important, but there's a room for improvement, I think.
Fantastic. Maybe moving to the anticipation, the NVIDIA team. I'm wondering whether we will be able to bridge this gap. You can see now where recognition is. We're able to get something like 52% on action, and anticipation is still struggling to get 20%. What do you think is needed to kind of start bridging this gap between these two problems? Or is it not bridgeable?
Yeah, I think there did have some gap because for the action anticipation, I think the problem is super difficult is because the supervision target is with very limited information, and also the relationship between the observation and the supervision target is very weak. And sometimes the observation frame is even not with a meaningful things in there, because it's just a one stop of the target target action. So, and we also fighting with the uncertainty, because the future is with many possibility. So I think what we should do next is trying to leverage as much information as we can. For example, using the longer context, or trying to leverage multimodality, even multitasking. And I also think that it is a patient problem is not to map the observation frames into the action. It is trying to find out why the person in the video is will lead to the future action. So I think this is the very critical part to closing the gap.
Yeah, very true. Whether you know the goal and where they're going. I think what excites me every time when we present these talks is the level of novelty in the approaches. So, you know, in some challenges, it's all about putting stuff together. And here we're seeing approaches that are really looking beyond either modalities, long tail, really exciting works. I think it's time to move to the second set of winner talks. And I think next we have the action detection winning team, who I believe are joining us remotely. Yes. Oh, there is a question on the text on anticipation. So maybe the teams can answer it on text in the meanwhile. So if you're on the chat, you can also be able to answer the questions. Thanks, Grace. So if you would like to share your screen, we're ready for your talk. Yeah, we can see your screen. Looks like we can hear you too. So
Hi, can you hear me?
we can hear you very clearly.
Okay, thank you. I'm Li Jun, and I'm from Alibaba Group. And today I will give a talk about our approach for the action detection challenge. Our team member are me, Lian Zhuo, and Wang Zhang. First is a task definition. Action detection is very hard comparing to the action recognition, because given one video, we not only need to recognize the action category, but also temporarily localize the time boundaries. On the other hand, the application is also very difficult data set. not only contains the verbs, but also the nouns. Most of the application clips are less than 20 seconds. There are two main approach in action detection. The first is the two-stage method. The other is the one-stage method. The two-stage pipeline is first using snippet probes to construct proposals and then classify the proposals. Here is an example of the structured segment networks. You need to construct the probes first and then use another network to classify the probes. The advantage is this kind of approach is more accurate, but the disadvantage is it is complicated and not differentiable and is much slower than one-stage approach. The other is the one-stage approach. It can directly regress time boundary and classify the category. Its advantage is end-to-end and simple and fast, but is usually less accurate. Here's our solution. We propose a simple pipeline, which is one stage. Given one video, we fed the video clips to the video encoder, and we can get the clip embeddings, and then the clip embeddings are fed to the transformer encoder to get spatial time representation. And the last is the detection hand. We have classification hand and the regression hand. We simultaneously predict the verb and the noun, and the action probability is computed by the probability of verb and the probability of the noun. And then it's our loss functions. The classification loss is the combination of verb, noun, and action. The other is the regression loss. On the bottom right is the architecture of the transformer encoder. For video encoder, we have different feature extractors. Omniverb, motion former, multi-scale VIT, slow fast, and the transformer. We use different feature extractors to get different features and then construct different models. After training the model, and we use the soft NMS for post-processing. It can remove redundant instance according to the verbs. Here is the results on validation set of different feature extractors. And we can see the Omniverb achieve the highest score in MAP. After we train the 5 models, we example the action instance results from these models, and we can reach 24% on the validation set. From the tab, we can see we have a much higher performance on verb, and we can get 21%, a little bit than 21% on mean average precision. The last is the conclusion. One stage approach can also be competitive with two-stage approach, and video feature plays a very important role action detection. Ensemble can greatly improve the mean average precision. That's all.
Fantastic. Thank you very much. We're moving directly to the second. Yeah, thank you very much. Congratulations on winning. Moving to the second talk for action detection. We also have a virtual talk. If you can share your screen. Some minor issues. Okay. Move to the next and then come back. Okay, let's move into the winning team for unsupervised domain adaptation. And I believe they are virtual. The second team are in person. The first team, we're just shifting for technical difficulties. Thank you. If you unmute or turn your camera on, we can see you then.
Okay, please wait a moment.
Yeah, we can see you indeed, but we
Okay,
can no longer.
then
see
I
the
will
slide.
start the sharing.
Excellent, go ahead.
Okay. Hello, everyone. This
We
is
sh-
Yicheng from.
Currently, wait 1 second. We currently see your presenter mode. You probably want us to see the other one.
Okay. Sorry.
Yeah,
Okay.
fantastic. Go
It's
ahead.
okay now? Okay, thank you. Hello everyone. This is Yicheng from A-Star Singapore. Today I'm going to share our team via I2R solution on the Application 100 UDA challenge for the action recognition. This is a joint work from me, Dr. Lin, Dr. Fang, Hao Xuan, Dr. Xu, and Dr. Sun. Here is the outline of my presentation today. As we know, the goal of this track is to adapt an action recognition model trained on a labeled source domain to an unlabeled target domain. However, there is one intrinsic limitation of the existing method. That is, they directly align the source and target features. We think this would introduce extra noise and reduce the discriminability of the learned features, as the source video features contain both the action relevant and action irrelevant features. So to address this limitation, we propose an action-aware domain adaptation framework, which leverages the prior knowledge induced from the action recognition task during the domain adaptation. Also, we exploit the verb-noun co-occurrence matrix to constrain and refine the action predictions. Here is the outline of the proposed framework. First, the frame-level video features are extracted from the video frames using a pre-trained feature extractors. Then the extracted features are passed to a GCN, followed by the average pooling to generate the video-level source and target features. Next, the video source feature is passed to the action classifier, and then the action discriminative features are generated using the action class knowledge learned by the action classifier. Lastly, we align the video level target feature with the action discriminative source features for the video domain adaptation task. During the inference, the video level target features is passed to the learned action classifier for the action prediction. Since each action class is defined as a combination of a noun and a verb, we design two classification branches, with one for the verb, with one branch to predict the verb probabilities and the other to predict the noun probabilities. Therefore, the action probabilities are computed as the product of the verb and noun probabilities. However, in this dataset, some action classes are invalid because certain verb and noun classes are incompatible, such as the verb rings and the noun table. Therefore, we propose to utilize the co-occurrence of the verb and the noun as the prior knowledge to refine the final prediction on the target samples. Concretely, we compute M, the co-occurrence matrix of verb and noun, from the statistics of the source domain, with the assumption that action classes never appearing in the source domain are highly likely to be invalid. We refine the action probabilities on the target samples by reducing the probabilities of the invalid action classes. Here are the experimental results. As we can see, Table 1 shows the ablation study of different components. It is observed that both components are effective in improving the model performance. As shown in the below table, by example, the results from different models, our final results rank first on the leaderboard. In conclusion, we propose an action-aware domain adaptation framework that leverages the prior knowledge induced from the action recognition task during the adaptation. To further improve the action prediction performance, we exploit the verb-noun co-occurrence matrix to constrain and refine the action predictions. With further performance improvement from the model example, our final submission ranks first on the leaderboard in terms of the top 1 action recognition accuracy. Yeah, that's all from my presentation. Thank you.
Fantastic. Thank you very much. We will go to questions after we do 2 more talks. So we're moving back.
Okay,
Excellent.
thank
Well done. We're moving back to the second ranking team in detection. Hopefully problems are sorted and you can share your screen. I think, Cheng, you need to unshare your screen. So, yeah. Can we try that? Yeah.
Okay, so can you see my screen?
We can see your screen. We can hear you. Go ahead.
Yeah. Hello, everyone. I'm Chen-Lin Zhang from 4Paradigm. Today, I want to introduce our submission to Applications 100 Action Detection Challenge. Our team includes myself, Ling Sui from Nanjing University, and Abbar Majedi with Vanasha Reddy Gajala and Ying Li from University of Wisconsin-Madison. Temporal action localization is to identify the onset of action instances and at the same time recognize their categories. Several recent works have developed deep models for temporal action localization, but none of them are especially designed for first-person videos. Shortly before the Applications competition, we developed and posted a work named Action Former. Action Former is also in the first place of their presentation. And Action Former adapts a transformer model to classify every moment in the video into either one of the foreground action categories or the background. If a moment lies in the foreground, the model further regresses its temporal boundary. This is a very simple model, yet with strong empirical results across major benchmarks. An earlier version of Action Former is applied in Applications 2021 Action Detection Challenge. Then we will introduce the process to detect egocentric actions with Action Former. First is the feature extraction process. We use 2 kinds of action recognition models, slow-fast ResNet 101 non-local model and the VI-VIT model. For slow-fast ResNet 101 non-local model, it is pre-trained on Kinetics 600. We fine-tune the model on the Applications action recognition dataset. For the VI-VIT model, we directly take the model from the last year's champion NUS team to extract the features. We feed 32 successive frames to extract features with stride equal to 8. Then we combine these 2 separate features into a final 72 dimension feature set. Now is the action detection phase. An action on Applications is defined as combination of a verb or motion and a noun active object. We train noun and verb prediction models separately with Action Former. Then we fuse the outputs of individual noun and verb predictions for final action predictions. We use the following rules to combine verb and noun predictions. For each point in the Action Former, we grab their classification score and predicted boundaries. And we use two weights, or alpha and omega, to form the final action and boundary scores. Alpha is set to 0.45, and omega is set to the normalized confidence scores. Now, let's look at our results. We first present our results on applications 100 validation set. The results are in the right feature. We list the baseline method, include BMN and the last year's champion. Our results are in green. Compared to published baselines, our models have a significant performance boost over all three subtasks. Our model achieves 22.7, 26.4, and 21.4 MAP on verb, noun, and action subtasks. Next, we show our result on applications 100 challenge. The results are in the right feature. In this feature, we have a slight 0.3 MAP gap with the top ranked method, which use stronger features. Our next steps will be using stronger video features and incorporating object detection outputs. To conclude, we explored using a strong and simple baseline action format for action localization. Our model achieves strong empirical results on major benchmarks. Our technical report is on arXiv, and our code will be released. Thank you.
People are using the best winning method from recognition to beat detection, domain adaptation for anticipation. I think this is very exciting. So over to you.
Hello, everyone. Our work is audio adaptive activity recognition across video domains. The original paper has been accepted at CVPR this year.
Do you want to maybe on your camera so people can see you online? Yeah, perfect.
In this work, we deal with the vision distribution shift by activity sounds. Here are two examples. The first contribution of our work is we propose an audio adaptive visual encoder supervised by audio balanced learning and absent activity learning. For the audio balanced learning, the motivation is videos from different domains often have different label distributions, not only in terms of activity classes, but also interactions with objects or the environment. So we propose to learn each class and each type of interaction equally. Here we provide an example. For the opening activity, we can see that the rare interaction in the source domain is more similar to the frequent interaction in the target domain. So for source domain data, we use audio to cluster samples inside each class. Then each cluster is treated as one type of interaction. We also propose an absent activity learning for the visual encoder based on the observation that most activities are silent, so the audio predictions are unreliable. However, we observe that the activities with the lowest audio-based probabilities are usually unlikely happening inside the video. For example, when the environment is silent, it's impossible that the activity is playing piano. Therefore, we force the model to predict low probabilities towards these absent activities. Here is an example. For the poor activity, we find the classes with the lowest probabilities by the audio is wash, close, and open. Besides that, we also introduced the audio-infused recognizer to incorporate the out-of-sight information from sound into the visual features for the final prediction. It includes a domain binding to remove the domain-specific visual features, and an audio adaptive class token that incorporates the activity information from sound. This is generated from the activity sound feature vectors. The motivation is simple because we find that some activities under the egocentric view happen out of view, but the sound is clear. For example, in this video, from the third person view, we can see the activity clearly. However, we can only hear the sound in the egocentric view. We first present the model components ablation. This experiment is conducted on the experimental setting from the CVPR 20 paper. We found that all components in the audio adaptive encoder and the audio effects recognizer contribute to the performance improvement under the distribution shift. And we also compare our method with alternative fusion methods and find that although within domain fusions achieve good performance, our approach provides more effective cross-model interaction and the domain shift. And when compared with state-of-the-art methods, we find our audio adaptive model outperforms the existing region focus with new domain adaptation methods. For the challenge, we make a few modifications to the original paper. First, we predict the verb and noun separately by different models because we found that the slow-fast network is good at predicting the verb activities. And then we use 4 models that are trained separately. Then average the predictions for the final verb prediction. But for the noun prediction, we find the omni-verb perform very good. So we train 3 transformer models and also average the predictions for the final noun prediction. During the competition, we find we achieved the best overall accuracy in the noun and the action predictions over all methods that report the results on both target and source domains. We conclude that activity sounds play a vital role under video distribution shift, and they can also help the visual model learn more discriminative visual representation. It can also, and our audio adaptive model provides more effective cross-model interaction under domain shift. More results can be found in the extended abstract session. Thank you.
Excellent. Excellent, thank you very much. If there are burning questions, otherwise I might, in the interest of time, move into the last bit, but if there is time for quick questions, I think for me, like the main message is how strong the features have been really critical in beating previous year's baselines. So recognition is really influencing. And then again, modalities are making such a big difference. And as I said, what excites me the most, I've always said there is one model that should solve all those challenges. I think we're getting closer to that. Let's move into the multi-instance retrieval. And we have Kevin, I believe, for the first. Oh, I need to share my screen. Oh, I am sharing my screen. Okay.
Hey, Dima.
Right. Hi, how are you? I think we can see you. We need to see your slides.
Okay, let me see my screen. Okay. Can you see it clearly?
We can. Go ahead.
Okay, thanks. And hello, everyone. I'm Kevin Lin. I'm incoming PhD student at ShowLab NUS. Today, I'm pleased to present our recent work, egocentric video language pre-training, and I will introduce how we transferred our VLP model to the multi-instance retrieval task. Our team member from ShowLab NUS and Tencent Data Platform. Video language pre-training driven by large-scale third-person dataset like how to 100 million has advanced a wide range of downstream applications, such as video text retrieval and VQA. But in the egocentric domain, there's no such counterpart since previous egocentric datasets are of small data scale and domain specific, making VLP impossible. And today, thanks to the introduction of Ego 4D, we can unlock the egocentric VLP. In our work, we explored egocentric VLP in 3 ways. Firstly, we construct Ego Clip, a video text pre-training dataset that contains 3.8 million clip text pair while chosen from Ego 4D. covering diverse human daily activities. Secondly, we devised an egocentric video text pre-training object, EGO-NCE, which extends inference with two novel sampling strategies. Thirdly, we construct a development set EGO-NCQ, which has less discrepancies with EGO-CLIP, powering us to validate our design of pre-training. This is the data flow of our egocentric VLP. We use EGO-CLIP to pre-train a VLP model with EGO-NCE loss, and then evaluate our model on EGO-NCQ. According to the feedback, we refine our design of EGO-CLIP and VLP model. And once we finalize the VLP model, we transferred our VLP model to the multi-instance retrieval task. And this task, we further equipping to this technology. We propose the adaptive multi-instance retrieval, multi-instance max margin loss for fine-tuning. And also we use the dual soft max from inference. Here, we display how we transfer our VLP model to the MIR task. Our VLP model is based on frozen in time, which consists of separate video and text encoders. After pre-training, we fine-tune the model on the MIR task by MIML loss, which minimize the distance between the positive sample and maximize the distance between the negative samples. However, in this loss, all combinations are treated fairly with the same margin. And intuitively, if two samples are very high similar, they should be put closer with a large margin over the negative. Otherwise, that should be put with a small margin if not very similar. So we introduce an adaptive margin to MIL loss based on the narration correlation to better distinguish the sample relationship. And after fine-tuning, we use the model to extract the video text feature and use the dual soft max to better normalize the similarity and get a final prediction. And here we first display the experience results by comparing the first person and third person VLP from different pre-training set, including the how to 100 million, CC3M, where we and our EGO-CLIP, we have three findings. First, EGO VLP significantly outperformed the third person VLP in both zero shot and fine-tuning. And second, EGO VLP beats the baseline, especially in NDGC, with fewer input frames and modality. And last, we find that our EGO VLP convergence faster than other counterparts. And the above results prove the strong performance of our egocentric pre-training. And next, we validate different strategy when transfer the pre-trained model representation. We found that the MIM loss is far better than the inference CE, since it is well aligned with the semantic repetition of this task. And second, with our proposed adaptive margin, we further boost the performance with a simple design. And finally, by equipping the dual soft max from inference, we reach the best single model performance. Despite our VLP brings some promising results in this task, we want to mention that the VLP requires a large training cost. That's all my presentation. You can find more details in our archive paper, and we will release the code and model in the next week. If you have any question or want to discuss our work, please feel free to send us email. Thank you.
I am muted. Okay. We're moving into the second. Thanks, Kevin. We're moving into the second multi-instance retrieval talk. And I believe Alex is with us.
Yes.
Yeah, if you can share your screen.
Yeah. Do you see me? Yep. Okay, let's see if I also share screen. Okay,
Yep.
so this, okay, perfect.
Go ahead.
Okay, thank you. So hi everyone, I'm Alex Falcone and I'm a PhD student at University of Udine and Fondazione Bruno Kessler. So our solution is motivated by a shortcoming of a typical learning setting for text video retrieval. In particular, 3 ingredients are usually used for this task. That is deep networks, large-scale datasets, and an optimization framework, which often involves a contrastive loss. In particular, one of these losses is a triplet loss, which is shown on the right and tries to increase the similarity of video V star and its own caption Q star, while decreasing at the same time the similarity with a negative caption Q minus, which is a caption not associated to V star in the dataset. So Q minus usually and often is selected as a hard negative. So a negative caption, which has a high similarity to V star in the current network state during training. Visually, we may have a situation like this one. And in particular, after performing the weights update, we may end up in a situation like the one shown on the right, where the video is more similar to close fridge than it is to pick up a bottle of wine, which intuitively is not good when looking at semantic similarities in video retrieval, since Q star is take bottle, which is quite similar to pick up a bottle of wine. So a technique that we recently proposed focuses on the margin of the triple loss, which is typically enforced between the similarity of the video and captions picked during training. By using a fixed margin, all the negatives are pushed away from the answer with the same magnitude, meaning that the loss treats them equally. Yet, a negative caption may be also partially relevant to the answer, as we show in this example, where multiple values of relevance are observed. So we propose to use a relevance-based margin, that is a margin which is proportional to the relevance itself. If you look at the example, this means that for V star, Q star, but also other captions which share the same semantic classes, we want to enforce a margin which is as low as possible. Then, with captions which are only partially relevant, we enforce a slightly higher margin. With captions which are almost irrelevant, an even higher margin, and so on. A second technique which we proposed recently puts the attention to the examples mining. So in particular, if we look at the R negatives equation, we see that also relevant samples may be selected by this technique, as can be seen in this example on the right. The strategy that we proposed consists of 2 sub-techniques. So first of all, we improve the negative selection process by defining it in a relevance-aware fashion, meaning that we move from a negative spool to a pool of semantically irrelevant samples by using the relevance function and a threshold value. So now, in a sense, we perform the negative mining in a more restricted pool of samples. Secondly, we also want to use the relevant samples during the training process, since they would be unused otherwise. To do so, we first introduce the hard positive mining, again by using the relevance function and the same threshold as before, and an additional loss term to actually drive the hard positives, which may include samples not originally associated to V star in the dataset, closer to the answer, therefore increasing their similarity. Since it deals with both negatives and positives mining, we call this technique relevance-aware negatives and positives mining, simply, or RAMP. Finally, to realize the solution that we submitted to the leaderboard, we used an ensemble of 5 models that we trained with these 2 techniques. In particular, these 5 models use HGR and JPose as base architectures, which are 2 interesting techniques for fine-grained text video retrieval. To perform the ensemble, we first computed the similarity matrix for these 5 models. Then we computed the mean, therefore obtaining a final similarity matrix where each of the similarity scores is determined by 5 experts that were trained with the 2 techniques mentioned before. By using this ensemble, we achieved a joint first rank obtaining almost 50% MAP and 61% NDCG. And we also released the code and pre-trained models for both the learning strategies on GitHub. And that's it. Thank you for the attention.
Excellent. Thank you very much, Alex. I suggest that we, if you have any questions, please put them on the Zoom. For the speakers, please check any questions you have on the Zoom. And in a couple of weeks, we will be able to release the full report, which includes details of all these winning entries. And I recommend, if you plan to submit to EPIC next year, to read this report, because it really includes lots of technical details that will help you to achieve good performance next year.